All right, so let's get started. We're talking about image matching. And we're almost done. I believe that we already started to talk about the inverse compositional algorithm, right? All right, so inverse compositional algorithm. So let's review very quickly what this is and just give the final solution. And hopefully you have practice at home, so you get practice over time about how to derive these algorithms. I mean, by now, it should start to be a little boring, right? Because it's all, we have this nonlinear equation, and we linearize it with Taylor. We take the derivative and equal it to 0 to find the minimum or the maximum, and we're done, right? So it's all about the same, but now you know that next time that you need to do that, you work for a company and you need to solve one of these problems, all you need to do is derive the criterion that you want to minimize or maximize, right? You want to optimize, linearize it, and then solve with least squares, right? It's that simple. Okay, so we had this inverse compositional algorithm, which we wrote down as Wx, W, the transform that I'm considering. In general, in image processing, this is going to be an affine transformation, right? The classical transformation that you're going to see people use is the affine, obviously. It's the one that makes more sense to us. This is given by Wx with respect to parameters theta, composed with Wx and the increment that I'm going to apply to these parameters inverse. And that comes from, or is represented as the sum over all the pixels x of t, the template, remember, that I need to match defining the image, Wx increment of the parameters that I'm going to apply, minus the image Wx, the current parameters that I have, all this squared. All right, so now the first order Taylor expansion of this criterion is given by, let's see, the sum over all the pixels x. Now first I have t, the template, Wx theta, right? And now I have this plus the excuse me, the gradient of my template times the partial derivative of w, my function, then my transformation, with respect to the parameters, right? Times the increment of that parameter, or parameters, minus I Wx theta, right? And all this is still squared. And if we solve for the increment, which I'm looking for, this yields the solution that my increment should be equal to the Hessian inverse, the sum over all the parameters of the gradient of the template times the derivative with respect to the parameters of W with respect to the parameters theta, transpose times the template, or the image rather, Wx theta minus the template. Okay? That's it. So it's the solution that I have. Now, the advantage in general, you want to use this inverse compositional algorithm compared to the others that we have derived here in class, because this algorithm is much more computationally efficient. Okay? So this algorithm has the advantage that is computationally efficient. Now, the result is obviously going to be the same as the other algorithms. There's no basic difference. But the efficiency of the algorithm makes it a preferred template matching algorithm in the literature. Okay? All right. Any questions about image matching, template matching?
So can you explain why it is computationally?
I would have to go back to, we have to derive all the other solutions and show the number of computations that you need to perform in each of them. I did post in Canvas the paper that goes step by step about all the computations that you need to perform in each of these 3 different algorithms that we have derived here. And you will see that for this one, the number of computations that you need to perform is slightly smaller, or significantly rather smaller. So, I mean, it's simple as that, the number of computations, nothing else. Any other questions? No? All right, so let's move on. I want to cover one last topic before we change gears to the last 1/3 of the course, and we cover a set of other tools that are going to be also extremely useful for image processing and computer vision. Now, I want to say this last topic I'm going to cover, I'm only going to sketch it. It's going to take a while, but I'm going to sketch it because it's getting complicated, right? It's getting to a point where we're getting into algorithms that are high level, right? They're getting a little tricky. You should be able to follow everything I'm going to cover here today. However, I will say this last topic, just what I'm going to cover from now on today, okay, for the rest of the day, is not going to be in the final, okay? Up to here, yes, but the rest of today is not part of the final exam. But I do want to cover this in some detail because I want to give you an example of things that you can do with these methods and algorithms that we have derived in class thus far, okay? Which is really cool. And this is called SLAM. SLAM stands for Simultaneous Localization and Mapping, meaning that I want to localize where I am at and map my environment simultaneously at the same time. And in particular, I'm going to talk about what's called MonoSLAM, which means that I only have one camera, okay, to do so. Now, this is, has a tremendous amount of applications these days because of robotics, right? So there are some of these, not all of them, but some of these high-end vacuum cleaners that are robots that you press a button and it cleans the room for you, right? Or maybe the house. If you don't have stairs, they can still not go up and down the stairs. But other than that, they can avoid pretty much everything. And some of these high-end robot vacuum cleaners actually use MonoSLAM to know where they are, map the environment, and determine how to navigate around, to optimally navigate around and make sure that they clean the whole room. Okay. Now the original ones were just completely random, right? You move randomly, and because of the loss of randomness, you cover most of the space, right? It just takes longer, but you cover most of the space. But in the high-end vacuum cleaners, now you have this MonoSLAM that allows you to simultaneously know where you are at and reconstruct the world. So I want to briefly cover, as I said, this topic and show you maybe a couple of videos of things that can be done with this. Another obvious application of this technology is self-driving cars, right? You want to know where you're at, and you want to map your three-dimensional world, right? So we're going to combine a lot of things that we have seen, like camera models, like ideas from structure from motion, and so on, that are useful for this image matching, obviously template matching. So what I'm going to introduce is basically an earlier form of MonoSLAM that uses basic template matching, meaning that I'm only looking for some specific landmarks in my environment. And now these days people do what's called dense SLAM, which means that you basically recover most, if not all, the points of your environment. Okay. All right, so again, SLAM stands for Simultaneous, Localization, and Mapping. So our problem is to construct a representation of our environment. Our environment is unknown to us, so we need to find a representation of the unknown environment, right? Now, find or define a representation of the unknown environment. Okay. Now, this is obviously, as you know, really hard. So we're going to need to make a lot of assumptions, or we're going to need to add a lot of help. We're going to need help to solve this problem. Now you will see that in SLAM people claim that this has to be real time. That is partially true, but it depends what you mean by real time. So if you go to computer vision, if you take my class in computer vision next year, real time generally is considered anything that can work faster than 30 frames per second, okay? Or 25 to 30 frames per second, because this is usually the minimum frame rate that you have in a decent camera, right? So if you can process 25 to 30 frames per second, you can process enough data, right, to respond in real time. But in these robots that I'm describing here, that is misleading, right? Because if I'm a vacuum cleaner, my real time means that I'm not going to move until I know what I need to move. So, you know, it may take me an hour to process that information, and then I decide where to move, and I can still call this real time because I'm not moving. So it all depends how you define that concept. It's a little strange. So I want to do this while at the same time, right? While concurrently estimating the camera's position. Or, I'm sorry, not position, ego motion. So the ego motion is the motion of the camera, right? So if this is my camera here, the motion that the camera has, that is called the ego motion, right? The motion of that particular object or robot or camera. SLAM generally defines this representation here as a probabilistic map. And it typically does this with a Gaussian model. Now in 1D, you will know that a Gaussian looks something like this. In 2D, if this is my 2D, these two axes here are my 2D, then it looks something like this, right? Three-dimensional Gaussian. But you will usually see it drawn in an image as just that ellipsoid here, right, in the center. Okay, so let's define this representation, this representation or this map. So we're going to call this map, say, XV. And this is going to be, let me say that this is the camera's state vector. How about if I say that? It's a camera state vector. And to define this, I'm going to use a variety of parameters. The first one that I need is the camera's 3D position, okay? So let's say that I use RW as the camera's 3D position. Okay, so the first element here is going to be RW. Okay. Then I also need to know the world coordinate system, and I'm going to use a vector QR, which is the orientation or the vector in the world coordinate system. So that I know where the camera is in my world, right? So that's another set of parameters that I have here. What else? I'm also going to define the velocity that the camera is moving at, okay? So my velocity of the camera, velocity vector. And the velocity just tells me how fast or how the camera moves, but the camera has also some angular velocity, right? So I'm going to define this as omega r with respect to the camera. This is the angular velocity vector. So let me add those here. All right. And that's my vector that defines the camera state vector. Okay? See that? Okay, now what do I need? This is the camera, this is information of the camera. Now I need the landmark points in my world, in my three-dimensional world, right? So let's consider those. So let yi be my three-dimensional points, so defining R3. So this would be the coordinates vector of the landmark points. And those are defined with respect to the world coordinate system, right? Okay, so I can now generate a final vector, let's call it x hat, for example, that has the camera state vector and my landmark points. Let's say I have n landmark points, so y1 through yn. Okay? All right. Now, this is a very difficult problem. As we should know by now, right? This is extremely hard problem to solve because I need to find all these parameters, right? So I have just one camera that is moving in my world. I don't know anything about my world. I don't know what velocity the camera is moving. I don't know the angular velocity. I don't know any information about my landmark. I have to find all this. By now, I hope that you know that that's impossible, right? So we need to make some assumptions. First assumption, typical assumption that we have made before. I'm going to assume that my world is rigid. Okay? The environment I work in is rigid. My world is rigid. I cannot deform it. I don't have a person moving his arms in there, right? And the landmark point is just deforming with respect to other landmark points. That would be really hard. Same thing that we did with structure from motion, right? No different. Or anything else that we've done. Shape from shading. All right, I need to make more assumptions, a stricter assumptions than this. Because you see, this is scene that I have right here, right? Is rigid. You agree? But I can pick up one of these rigid objects and put it somewhere else, right? And now everything, the environment has changed again, right? So I can allow this. So I'm going to say that the 3D world landmark points do not move. So all my landmark points are static. Now, there's an underlying assumption that I'm not going to write, but there's an underlying assumption you may want to write, inherent in the formulation that we have to define here and that we have derived in this class over and over again, which is that the camera motion is given by a translation vector and a rotation matrix, right? We accept that, okay? That's the reality of the Euclidean space. So that is also inherent in our derivations. I'm going to consider the world coordinate system is at the initial position of the camera, or at the camera's initial position. Okay? At the camera's initial position. All right, more assumptions. I'm not done. This is how hard this problem is, right? It needs a lot of assumptions. where's a typical problem that we have when we want to recover the shape or the structure of our environment or of an object? Well, what's that? We're not going to assume affine transformations here. We're not going to assume we're in the affine world. We can recover, we know that we can recover the structure of the scene, right? But we have a limitation, which is the scale. Very good. Someone said that, right? It's up to scale, always. There's no way we can solve it beyond that. Well, there is a way. If I have an object that I know its size of, then I can solve for the scale. But I have to have that object, right? So that's what these robots have. They have an object, right, in the package that you put in the, when you plug them in and, you know, they sit on the floor of your room. They have an object, right, and when they pull out, they look at some structure in that platform, for example, that they know the exact measurements of, right? And from that, that's where they start. They get the size of the room, right, the scale parameter. So we're going to assume that this is given to us as well. So we're given an object of known size. We're also going to assume, even more than this, that some of the landmark points in my environment are already given to me. Okay? So we have a few landmark points. Still more. Still more assumptions. I'm going to also assume that the camera moves at quasi-constant velocity, right? And that's something that in a robot I can control. That the velocity doesn't change dramatically from point to point, right? That if I have an acceleration, it's very smooth and very slowly changing, right? So quasi-constant velocity. And the acceleration that I have, I'm going to assume that it's given by a Gaussian model. Now, a Gaussian model in the acceleration means nothing else than the change in velocity or acceleration is smooth, right? That's all it means. Doesn't mean anything else. So that I don't have all of a sudden something that moves very slowly and then moves really fast and then slow again and then fast, and that there would be non-smooth. All right, that's it. That's all the assumptions I have. Okay. Now with this, I can solve the problem. It's crazy, isn't it? But that's all I need to know. All right. So let me define the vector n that is given by, let's see, the acceleration, AW. And that acceleration I'm going to consider for every increment of time. And the angular acceleration, let's call it alpha w, also increment of time, right? So this is my velocity that I'm moving at. And n, it's nothing else than that velocity that I'm moving at times a small portion of time, right? Differential of a time. And the same for the angular velocity. In fact, why don't I just call the velocity, I'm going to call it v, and the angular velocity, say, omega. Okay? Now, I actually lied. I need one other assumption here. I'm going to assume that the velocity and the angular velocity are uncorrelated. Now, if you don't know what that means, forget it. Doesn't matter. Take some of my other classes and I'll explain it in detail. But if you know what it means, you'll understand the equations a little better. OK, so now we have everything that we need to update our map. And the update of the map is going to be given as follows. Now, first, we're going to go to R, which is the camera's 3D position. Okay? Now, the position of the camera is going to change over time. I don't know what I use subscript here. I'm going to put RW as RW plus the change that I need to apply to this. And what do I have? Well, I'm going to have v, my velocity that I have defined here, right? That velocity determines where I'm going to go at, plus something else, I'm going to find in a second, times my increment of time, right? Excellent. Okay, let me just call this term here, I'll call it capital VW. And Q of the world is going to be given by, now remember Q was given here, which is the orientation that tells me where I'm in the world, where I'm at. That is going to be given by, let's think about this. This is where I'm at now, plus after I move, this is going to be given by Q of WR plus omega r times the differential of time that has passed. Okay. The velocity is going to be the velocity plus this term of how it changes. And the angular velocity is going to be the angular velocity that this changes at, right? Now with this, I can predict where I'm going to be next, right? So if I have a certain landmark, the position of a landmark point is going to be given by, let's see, if I have yi, right, one of these landmark points that I have in my world, then what do I need to consider? I need to consider the translation. So I'm going to consider the translation here. And then I need to consider also the rotation, which I can write as a rotation from R to W. And I can write this as my predicted location. And that I can write it as 3 values, right? H, Y, and z, the coordinates of where I think I'm at. And if I apply this equation to a perspective camera, then I am going to get HI, which is the UV position in my image, right? Because this is the three-dimensional point in the world. So in the image, I'm going to have U0, V0, which were the initial positions of my landmark point in my previous image, minus Fk times HXR over HZR, and V0 minus Fk HYR over HZR, right? And this is the focal length of the camera, right? These are the x and y coordinates divided by the z coordinate, right? And this is the aspect ratio of the camera, right? That's it, right? So those are the expected coordinates. And one final thing. The camera motion actually, let's think about this for a second before we derive the equations. So imagine that I have a patch, right? This is my patch. This is my landmark point right here. And this is a patch of my landmark point, right? And that patch is given by vector n, right? That tells me where that patch is. And let's say, as always, that I take a picture of this. Now, if I take a picture of this, then I'm going to project this through the pinhole here, right? And that pinhole, remember, let's say that this is the first image, so that this pinhole defines the world coordinate system, which defines the x, y, z coordinates, right? And here I get my image point, my UV. And now I move the camera, right? I translate the camera, I rotate the camera, and I take a second image, second picture of that patch, right? I apply a translation and a rotation. Now the translation, of course, is given by simply the translation, the distance, right? The vector between the pinholes. And now here I project this onto the second image, and I get my new UV vector, right? That's what we have. And now if I want to predict or compute the information of this landmark point given that other one, I need to apply, yeah? Anyone? This is what you did in one of the homeworks. Remember when you had to rectify the image? It was tilted image, and you had to compute the frontal view. That's the same. It's called a homography, right? And so you need to compute this homography, which is given by CR n transpose XP I minus Tn transpose C inverse, where, let's see, C, this is, anyone can tell me what C might be in a homography? It's the camera's what? It's a calibration matrix, right? So this is a camera's calibration matrix. T is a translation, obviously, or it's a rotation. I here is a 3x3 identity matrix. And XP is our vector that defines all the information that we have. And N, it's a normal vector of that patch, right? Or the vector that defines the position. So with all this, you can create a map of where the camera is, how the camera is moving, and where I'm at with respect to the world, and then add to this, add to this all the landmark points, right, with respect to some world coordinate system, right, that I have set out to be the first position of the camera, right? And once I have this vector, I can compute, given the velocity that I compute, right? Given the velocity that I compute of the camera, the translation and the rotation of the camera, I can compute where the landmarks are going to be. And I can keep track of things. And because I'm moving in space, I can reconstruct the world in 3D as in a structure from motion, right? Same way, same thing. So let's see a couple of videos of this. All right, so this is a camera. This is the camera that we want to model. So this is the translation and rotation of the camera that you see here, right? So again, it should probably be smoother than this. There's some accelerations here that are going to break down the equations, but we'll see how it works, okay? Now, this is the landmark points that are being tracked by the system. And again, using template matching, same as we have derived here. This is another set of images, landmarks shown here. And then these ellipsoids basically tell you the likelihood that the point is in that region, right, of the patch. And now this is the three-dimensional map reconstructed, right, of all these patches that you are looking at. So you're reconstructing the 3D world as you move around. And now that you have this is just classical meaningless application. Well, actually, there are good apps now for this, right? You can actually, some furniture stores, for example, have an app that you can point in somewhere in your room, right? And it will play some furniture in that room, right, in the picture of the room. So it gives you an idea whether you want to buy that bed or couch or what have you, or chair. So here you're placing, say, this object in the image, right? So you see these objects like furniture that you can add onto the world, right? And then can determine whether you want to buy this or not. or where you want to place something that you bought, right? So this is actually pretty cool because people like to do online shopping these days, but furniture online shopping is still a few years or generations away because we need to get accustomed, not because it's not possible, we just need to get accustomed to using these apps to see how things are going to look in our room rather than having to drive ourselves to some store and spend time looking at the actual furniture there, but not in our room, right? I think that in general you prefer to see it in your room. So that's pretty robust to changes of velocity. And you can see some errors occurring when this happens, right? You see the landmark points being lost at some point, but it recovers pretty fast. That's a little dizzying. Some occlusions. All right, this is how bad graduate students are at cleaning things. And now here you're going to see the trajectory of the camera in the 3D world coordinate system, right? So this is how the person is moving in 3D world space. So this is the location that you're simultaneously recovering. So remember, you're recovering both the structure and the location of the camera. And here's an example of what's now called dense SLAM, which means many more points. This is pretty close to state of the art, and this is a reconstruction of a road map in a city from a camera located at a car. And you can see that the pixels obviously are really large. There's only so many computations that you can perform before the algorithm just takes too long. But it gives you a good idea of what the environment looks like. And you can see some errors, right? There are outliers here and there, obviously, but it's getting pretty good, right? And this would be the three-dimensional map seen from above of the trajectory that that camera took to create this 3D world. All right, back to the first position. So you get an idea how these things work. This is now very popular again because of the applications, the possible applications that this has in robotics, especially in robotics, also in self-driving cars, but most importantly in robotics, and most importantly at home. This is a comparison of the ground truth that's shown here in red and what was estimated by the algorithm. So all this, again, a lot of applications of this technology. I'm going to show you maybe a few extra examples of the algorithms or where we are at in research with regard to these algorithms that we have discussed in the several weeks that this course has been going on. There's still an intense area of research, obviously. We can do a lot of things already, but it's not perfect. You can always get better results, more dense, faster computations, right, and so on. So as I said earlier, you can buy a robot these days that vacuums your house. You know, it's pretty good, but that's pretty much it, right? Even those robots are not perfect. Not only they are not perfect, they don't clean that well. I mean, they clean okay, but not as well as a person. They don't do the dishes, right? They don't load the dishwasher. They don't unload the dishwasher, and so on and so forth, right? They don't move furniture. So we are a long ways off, right? When you hear in the news that AI is going to get rid of all our jobs, it's because the people that say that don't know anything about AI. Now, is AI going to eventually displace the work, meaning that not that it's going to take our jobs, but that we're going to have different jobs, right, in the long-term future? Sure, of course, right? We used to be, I think in the US about 75% of people used to be farmers. Now it's like what? 10%? I don't even remember what it is, but it's a tiny, smaller than 10% most likely, right? Tiny amount. So obviously over time jobs change. There's nothing wrong with that. But the process of eliminating jobs that we have right now because of AI is going to be really slow. And in fact, my prediction is that AI in general is going to create jobs. It's not going to eliminate. So it's going to change the type of jobs that we do. But as with the Industrial Revolution, as with the information revolution, the data revolution, this is only a way to create jobs that we can not even think of right now, right? But that will appear because we have this technology available to us. So there are many applications in the future. This is a great time to be working in these areas, image processing, computer vision, and machine learning. So I obviously would encourage you, if you're interested in these topics, to next year take computer vision and machine learning so that you expand your knowledge. You just don't get the very basics because this is the very first course, right? Image processing that introduces basic concepts, but we get in so much more detail in these other advanced courses on what can be done. And then obviously if you really want to work on this, doing a master's thesis or even a PhD in this area will get you all the necessary background knowledge. You're going to gain all the background knowledge that's required for working in these specific technology companies. So these that I have here in the slides are just a very few examples of papers that have been published this year. Okay, so these are 2018 papers, very recent, and just to give you an idea that all these topics are still very active in research. We're making tremendous amount of progress, but there are still strong limitations that only allow us to apply this technology to very specific problems like the vacuum cleaner, right? Self-driving cars is a technology that is coming. I I can't wait. If I have to tell you the truth, I can't wait to have a self-driving car. I mean, if there is something more boring than driving, let me know. I've never, oh my God, seriously, you know, have to drive to, say, Pittsburgh, which is right here. It's like 3 hours, right? How are you doing 3 hours behind the wheel? It's like, yeah, the first hour you listen to podcast, and the second hour you're just like screaming. It's boring. So obviously I'd be the first one to hope that I have a self-driving car. That is at least 10 years away, at least. Now, self-driving technology is improving rapidly, and we're going to have semi-self-driving, or more than semi-self-driving, I'd say some technologies that will help us drive better, right, or more secure. But self-driving, meaning from point A to point B, you don't do anything but just say, take me to point B, right? That is at the very least 10 years away, and I wouldn't be surprised if it's much more than that, right? I mean, it's very difficult to predict what's going to happen 10 years from now. That's a long time, but it's a very hard problem. Very, very, very hard problem. So one of the problems, for example, that self-driving cars have right now is interpreting what other people want to do, right? And this is a recognition of intent, the intent of others. And this is really hard. Computers cannot do that right now. It's absolutely, or almost, right? Okay, almost. We're getting there. Okay. One of my students is laughing because he's working on this. So, yeah, we're trying to make them learn how to interpret the intent of others, but that's a very difficult problem. But the intent of others, obviously, is something extremely important, right, to navigate in the world. So, for example, one of the problems that self-driving cars have is that they get into a four-way stop, right? And you know the rules. You get in the four-way stop, and the first car that gets in, doesn't matter which lane, the first car that gets in is the first car to go, right? Now, of course, the law also says that you have to wait for a second before going to make sure that everyone is stopped, right? And what happens is that self-driving cars get to the four-way, and then people are not patient, right? 1 second to us is like an eternity. So the cars get stuck there, right? People start passing, they see the car is not moving, so they just go because they assume that the intent of that car is not to go. And then the solution, it would be, well, let's be aggressive, right? Let's go before the 1 second mark. But now you're breaking the law. Now a human breaks the law because, you know, we are human. That's the definition of human, I guess. But to design an algorithm in a car to break the law, that's a whole different level. So unless you can interpret, you know, what others are doing, it's self-driving cars. It's a huge problem, and many other problems, right? We in computer vision, using some of this technology that we have derived here in image processing, computer vision, we can detect signs, right? Traffic signs. So we can detect where the stop is, and we know that we need to stop here. Now imagine that you're driving in a highway, right? You're in, I don't know, I-65, driving at 100 miles an hour, and, I'm sorry, 100, 65, let's not break the law. 65 or 70, all right, maybe 70 miles an hour. And there is a track on the shoulder, right? A maintenance track on the shoulder. A maintenance track, sometimes they have a stop sign on the back, right? Hanging in there, because if they need to put it somewhere to stop traffic. Now the self-driving car doesn't know all this, doesn't have this knowledge, these concepts. So it sees a stop sign in the middle of I-65, and what does it do? It stops, then you say, oh no, but I'm an I-65, I'm in an interior state. I'm not going to stop in an interior state. What if it is a sign that requires you to stop? You know the difference, but the self-driving car doesn't. Right? Again, these are very, very difficult problems to solve. And data by itself is not going to solve these problems, right? There's much more than that. There was an old project in AI that was called CY, CY, and the idea was to design a database of knowledge, okay? And that database would allow you to reason about what happens in the world, right? So we'll give you basic concepts like, gravity always goes down toward the ground and things of that nature. They hoped, right, that was back in the 70s, that once you add this knowledge to the computers, that AI would become more intelligent, and that was in the 70s. Right? And computers are still not intelligent. So you can draw your own conclusions of what happened. So again, these problems are very, very, very hard. All right, so this is what a structure from motion looks these days. This is, again, a paper published this year, earlier this year. This is what's now called dense structure from motion. So it works on non-rigid objects, right? So this is non-rigid structure from motion. And you have a video sequence, as we have done here in class. But you can have a video sequence of, say, a face that is maybe rotating in 3D, certainly speaking or making faces. And you can reconstruct the face like that from that video, densely, pretty accurately, pretty reasonable. Maybe even some part of the hair in here, which is not too bad. Hair, it's very difficult to model, by the way. This is a problem that computer vision still hasn't really solved. We'll see, right? Stay tuned, as they say. And this is a piece of paper that bends, right? You bend this piece of paper, and then you can reconstruct the piece of paper and the bending. This one here is a very difficult problem. This is really difficult. I saw another one, which are the flags. So imagine that you have a flag out there in a windy day, and it's flapping in the wind, right? And you collect this in a video, and you want to reconstruct the shape of that object and the motion. That's a tough problem. We can do it, but it's a tough problem, right? So these are things that we're doing. A former student of mine, who is working now for a self-driving car company, so I should speak better of self-driving cars. She designed an algorithm that you can do structure from, similar to structure from motion, but from a single, you could do this, what you're seeing here with these objects, but from a single 2D image. And that involves machine learning algorithms. So if you are interested, you can take machine learning and you'll learn about it. But there's a technique called regression that allows you to do that. And basically, what regression allows you to do is to create an internal model, right, of what, say, a face looks like, or a piece of paper looks like, or another car looks like. And then from a single image, you can see which is the best mapping from that model onto that image. And that will give you the three-dimensional structure of that object. So we can actually now recover the three-dimensional structure of an object, even from a single 2D image. I mean, that shouldn't be totally surprising. You can do that, right? If I only show you this 2D image, you're not going to be perfect, but you can get an idea of the three-dimensional structure of that human head, right? Why? Because you have enough experiences with human heads to know what they look like. So a machine learning algorithm can do the same thing, right? So that's how these things work. This is the same paper. It uses manifold learning. Again, this is something, or part of manifold learning, something that you may want to learn in machine learning if you take that, to define different components of the phase. But the important thing for you is to know that it takes the video sequence as we have defined it and represent this in a feature space. Now, the difference between what we've seen and this that is most classical now is that the structure from motion that we have seen, because it's rigid, you define the different images of the video sequence, right? And those define a subspace in your parameter space, right? Remember? And that's why we use SVD or eigenvalue decomposition to find that hyperplane, right? That defines the motion and the structure. This is the same idea, but instead of finding a hyperplane, you find a nonlinear manifold. Okay? So it's like a nonlinear extension of that. And that allows you to recover deformable objects. I had a former student of mine also that did some of this work early on, or one of the first works, if not the first, to define nonlinear, to estimate a nonlinear manifold using techniques like this. And he works at Disney, Disney Research, where they actually design methods like this to animate movies, right? And I'm not talking about animation, but actual real human movies, right? But you still have to generate. So if you've seen Star Wars, I don't know which of the latest ones. There are so many these days. When I was a kid, there was one every 5 years or whatever it was. Now there's like 2 a year, right? It's crazy. But in some of these latest movies, you have characters that appear that are no longer with us. These are dead people. And you see them in the screen, and you're like, what happened? How is that possible? Well, this is possible, right? And that's what my former student and many others do. They design these algorithms that allows you to do this, to actually create these three-dimensional models that can give you really nice reconstruction of a person, even if the person is no longer alive. This is from another paper, recovering the three-dimensional structure of a person. This is very difficult to recover the depth map, three-dimensional information of all the points that define an object like a person. And note that there are positions here in the shirt or the sweatshirt or whatever that is, right, that have different z values. So the depth of these different points is different. That's extremely hard to solve. This is a really nice work from a friend of mine that is actually considering repetitive motion. So imagine a person walking, this structure from motion still, but when a person moves, the motion is periodic, right, basically. And then here you have matrices that actually define, let's see what it is, periodic motion, which should be like this, right? So over time, right, the motion keeps repeating, the motion pattern. So you can actually take advantage of this when solving the equations of a structure from motion. You can simplify the equations and be much more robust at extracting that information. This one here is recurrent motion, and this one is a rigid scene, right? That only has the diagonal, obviously, elements. So from this video, this is the three-dimensional reconstruction that they create, which is pretty cool, I think, with this. Also shape from shading. This is given an initial gross estimate of the depth map and an image, can you create a nice three-dimensional model of the object? Pretty cool. Template matching that we have been talking about. this is this huge area of research. It's always been, obviously, tracking, finding. So if you want to do tracking of objects in a video, if you want to find an object in an image, right, you have to use template matching. I mean, that's what template matching is about, right? So if you want to do a stereo vision, structure from motion, you need to have template matching, and so on and so forth. So template matching is very important. And here are some examples of recent results, different papers. Now consider this video right here, or this video here, right? So consider this object that you're tracking here. Here is in basically darkness, right? It's almost black. Here you have a blue background, here a red background. I mean, it can get really hard to track these objects, right? Here the camera is moving, so the object starts looking almost frontal, then at some point becomes a lateral view, and then at some point may even become a backward view, right, of the object. So the information you have in your pixels, in your template, right, the template would be the box around that object, keeps changing over time, and you need to keep adapting to that change. So these are very difficult problems that are pretty much solved by now, but they're hard. They're hard problems. This is again template matching, finding point correspondences between images. This is template matching in depth maps. This is depth information, right? This is only the z values of all the points of your environment, and you have to find point correspondences here. Pretty cool stuff. This I really like. This is really cool. This is template matching for similar objects, right? But different images or different species of birds or different identities of birds, if I can say that. So, I want to find these different fiducial points in this bird and the corresponding fiducial points on that other bird, right? And they're pretty much similar in shape, right? But obviously everything else is different, right? The pixel values around of the window, the template around this point is going to be very different than this one around here, right? And people have figured out how to actually solve this problem. So the new template matching algorithms, the very latest, again, this is just published this year, are actually able to do these amazing matchings, right? Which to me is stunning. And you can even apply to different objects that look sort of the same, right, from a side view. For example, you have a cow here and this weird plane, right? And you can find, okay, this point corresponds maybe to this one here, and this point, I don't know if it's shown in here, but you get the idea, right? And the same with the bicycle. It doesn't work that well, obviously, but one could claim that there's no point correspondence here, right? That there's no point in that bird that is going to correspond to a point in that dog. But anyways, you get the idea. But the cross here, right, then that's it's sort of more realistic that this point may correspond. If it defines an ear, it should define an ear here, and here if it defines the top of the head, it should define the top of the head here. So the rows should still be consistent. People are still working in camera models. Obviously, that's a never-ending problem. This is especially useful in photogrammetry, as I've mentioned many times. Not so important for image processing and computer vision, unless you want to work in the area of photogrammetry. But depending on where you work in photogrammetry, you want to be so precise that you really need models of the camera that are really, really accurate, that really represent the camera. So here, this is not what this paper does. What this paper does is a problem that I showed you earlier here in class, that if I'm given several images of the same object, but these images are taken by different people, right? And maybe they post these images online, and this is a famous landmark in the world and a famous city. Then from all the images that I can find online of that church, Then I can find point correspondences with these latest algorithms to find point correspondences, and I can get the dense estimation of the 3D structure of the object like this, right? This is pretty cool, I think. This is also useful for conservation. So two ways to know what things look like, but also if you cannot visit all the wonders in the world, at least someday, we know not too long in the future, we're probably going to be able to see them in 3D with virtual reality, with our goggles, right? Virtual reality goggles. From the comfort of your home, you could just put the goggles on and move around your room and then be in there, right? In this world. And that would be really cool. If we have pictures of things that have been destroyed, unfortunately, because of war or whatever else might have happened to that site, we can still reconstruct them, right, with these techniques, if we have enough pictures. And we can still see things that no longer exist. So that's also pretty cool, I think. People do camera calibration from single image these days. As I said, we design an algorithm that can reconstruct the shape of the face, right? Can reconstruct the structure of the environment or of an object from a single 2D image. People are also doing camera calibration from a single image now, right? Now remember that if you have the calibration grid, you can do it too, but you need a calibration grid. People do it now from a random scene, right? And there are many things that you can take. For example, any horizon line that you can find, right? That would be the line at infinity that defines the projective space, remember? So those are things that are very useful. And so on. There are other things that you can use that are very useful to calibrate cameras, even from a single image. All right, I'll leave it there. Yep, right on time. We are going to start a whole new topic next week. So please do review everything that we've seen, because it's going to be in the final in some form or another, right? So make sure that you review, and if there are questions, let me know. And then we're going to turn to our final topic of the course. All right, see you next week.